Unit Operation Classroom, GATE 2023, question 30. Given that E in watt per meter square is the total hemispherical emissive power of a surface maintained at a constant temperature, which of the following statements is or are correct? First of all, uh, we are discussing a problem, but you must read a very good textbook to have a deeper understanding of this particular subject. So first of all, let's try to understand what is this total hemispherical emissive power, intuitively at least. Then we look into the mathematical definition of this one. Let's say this is part of the body, and what we do, so this is emitting radiation in all possible directions, right, and all possible wavelengths. So let's put a hemisphere on the top of it. So what is E? E is how much radiant energy is captured by this hemispherical dome, per unit area, per unit time. That means per unit area, how much energy is being radiated. So watt per meter square, that means this is joule per second. So that's the energy emitted per unit area, per unit time, per meter square of the hot surface. So that is my E. And there are a couple of options. Before that, let us try to have a deeper understanding about this problem. In fact, if you don't want to go for this deeper understanding, we can just go directly to the solution, which is given slightly later on this video. Or otherwise, you can just look into the basic theory, which is discussed in very briefly here, so that we can understand the problem or answer the quiz properly. Again, read a textbook. These are not sufficient for a student's understanding. So let us assume this is my hard body here, which is emitting energy in all possible direction and in all possible wavelengths, 0 to infinity. And this is my hemisphere. And this, of course, is a small area right here. And this is, of course, given by the solid angle. We'll look into it. And so the solid angle is omega. So that is by definition, by geometry. This is a sine theta, d theta, d phi, where theta, of course, is the polar angle, and phi is, of course, the azimuthal angle. And this is my d phi, and this is my d theta. So E is E given by this particular equation right here, and we'll look into it. What is what? Okay, what is E? What is this one E? E is, first of all, its unit is watt per meter square. That means total energy emitted per unit area of the body. And here you see E is the total radiant energy emitted per unit area per unit time, integrated over all directions in the hemisphere and over all wavelengths. So that is my E. Okay, integrated over all possible directions in a hemisphere and in all wavelengths. Integrated over all possible directions and for all wavelengths 0 to infinity. That is my E. We'll look into what is E lambda and what is I lambda. Okay, so what is I lambda? This is a function, of course, of the polar angle and azimuthal angle. This is called spectral radiative intensity, which is the energy emitted per unit area of the projected area. That's why that cosine theta comes in. Per unit solid angle, that is this omega. Per unit wavelength, that is this lambda, in a given direction, theta and phi. So unit is watt per meter square per steradian and meter of the wavelength here. Okay. So that is my I lambda here. Okay. So if we just integrate over the entire hemisphere, then of course we get E lambda. That means the energy emitted over the entire direction, all possible directions, but for a particular wavelength. That is E lambda. Okay. So as we said, theta is the polar angle, phi is the azimuthal angle, and cosine theta is, of course, because this has to be, there's a projection, so that's angle theta. So that's why this cosine theta comes in. We all know that. And lambda, of course, is the wavelength of radiation. So how can we say what is E lambda? This is the spectral emissive power, which is E lambda right here. This is my E lambda. In this equation, this is E lambda. So E lambda is just the integration over the entire sphere for any particular wavelength. Lambda plus lambda to lambda plus minus d lambda. So that's also in a small range d lambda. So this is my E lambda. Okay, so this is basically the integration over the entire this one. Okay, now this has to be, this E lambda has to be integrated over all wavelengths, that's 0 to infinity right here. Okay, so how do you say about E lambda? E lambda is the spectral emissive power, that is a per unit area, energy emitted per unit area per unit wavelength integrated over all directions in the hemisphere. Okay. All right. So we understand at least sketchily, even maybe, at least very vaguely. But before for a deeper understanding, you have to read the textbook. So this is my basic equation right here. Okay, and you can see these are the units here. Okay. Now, question is, how do you connect it to Planck's law? For Planck's law, this I lambda is given by the Planck's law, but for a black body. But for a black body, okay. And this Planck's law, according to this Planck's law, this equation is given by right here, where of course h is the Planck's constant, c is the speed of light, and lambda is the wavelength. So this I lambda is for a particular wavelength, spectral intensity for a particular wavelength lambda, and for a black body. And this is hc. This k is, of course, is the Boltzmann constant. So we all know about that. So for the EB, if we just write this one for a black body, that is EB, that is just everything. So this would be I lambda B, and this, of course, would be equal to E lambda B. And this whole thing is, of course, given by the Planck's law. Okay. So this I lambda B is given over the Planck's law, which is to be now integrated. And then we have from geometry, we integrate on this cos theta and d omega for a hemisphere. Then, of course, we get from there the E lambda, and that is E lambda B, and that, of course, has to be integrated over the 0 to infinity wavelength. That gives me total energy or total emissive power per unit area per unit time. Okay, so now let's quickly look into it. As we said, E lambda B, which is equal to, if we assume I lambda B, which is given by the Planck's constant, is isotropic. That means isotropic in emission in all direction, and I lambda B is independent of the direction, as we said. So I lambda B can be just this cosine theta d omega. And if we integrate that cosine theta d omega 0 to 2 pi for a hemisphere, this becomes equal to pi. Okay, if we do the integration, again, that is given in the textbook, the integration between 0 to 2 pi and 0 to pi by 2 for this polar angle and the azimuthal angle. So if we assume this to be constant, independent of the direction, so this becomes equal to E pi b. So this E lambda is equal to, for a black body, pi by b. Okay, and this, of course, is given by Planck's constant, we have seen. So this, of course, is given by Planck's constant. So E lambda b, this one is just you multiply by this pi here. So that would be the E lambda b given from the Planck's constant, of course, and do it over the entire, doing over the entire hemispherical surface. Okay, and so that is E lambda b, which is now has to be integrated over all wavelengths. So how do you connect it to the Stefan-Boltzmann law? For Stefan-Boltzmann law, for a black body again, the total hemispherical emissive power, according to Stefan-Boltzmann law, we are connecting now, is given by E lambda b d lambda over the integration over the range, and he said this is equal to Stefan-Boltzmann constant, which is a tip value T to the power 4, fourth part of the absolute temperature. Remember, this is the absolute temperature. So that's how this Stefan-Boltzmann law comes in. So again, quickly going back here. So this is, if we write this for the black body, this is given by the Planck's constant. This is integrated over the hemisphere. That gives me value of pi, and from here we get E lambda b, and this E lambda b, and when integrated over this thing, then gives me the Stephen Boltzmann law, the total hemispherical imaging. Okay, that's a very important one. Now let's connect it to the Wayne's displacement law. What is Wayne's displacement law? Is the wavelength for maximum spectral emissive power. Okay, so this E lambda b, as you can see here. Okay, so here's the hemisphere, and this is emitting in all possible direction. That's of course connected, taken care of that. All the direction part is taken care here, but this is for a particular wavelength lambda. Okay, now Wayne's law asks or makes this question that what is the wavelength when we have the maximum spectral emissive power. So basically we differentiate it with respect to lambda, and then he gets this equation here. Again, this is a wonderful constant, and as you can see, as the temperature of the body increases, this lambda max decreases. I'm giving you a very simple example. At 300 K normal room temperature, this is equal to becomes 9.66 micron. This is constant. So this is infrared region, no glow. As we increase the temperature, let's say 1000 Kelvin, it's around 2.9 micron, near infrared region, slightly close, dull red. Then temperature 1500, we get the near infrared, bright red, and T 2000, it goes into visible yellowish white glow. So this is the visible range, it just moves into the visible range from the infrared. Okay. So very quickly, so Planck's law gives me the spectral intensity for a black body. You integrate it over the entire hemisphere. This gives me spectral emissive power E lambda p. When you integrate it over all wavelengths, that's give me the Stephen Boltzmann law for a black body. Okay. And here, of course, at what wavelength this is the maximum, we get this lambda max T. So that's how they are connected. For a gray-body radiation, so we just take that spectral emissivity. We assume that E lambda is assuming that to be approximately constant. Spectral hemispherical emissive power, E lambda, of course, is equal to just multiplied by the emissivity. And total hemispherical emissive power for a gray body, of course, remains that by definition remains the same. For a gray body, Stephen Boltzmann law, we just multiply by the emissivity. That's just a slight reduction there. And for Wayne's law, this lambda max for a gray body almost the same as the lambda max for the black body. That's just a thumb rule. Okay. Now let us answer the question. Let's see, given that E is the total hemispherical emissive power surface maintained at a constant temperature. First one, E does not depend on the direction of the motion. As we said, E is, of course, as we said, is integral of 0 to infinity E lambda lambda. Okay, so that's the E. So this has already been integrated over all the entire hemisphere in all directions. That has been done, which is I lambda in cosine theta d omega, and we integrate over the entire range of the hemisphere. So we can say this E very quickly. Let's go here so that you have a better understanding. So this E, this was obtained by integrating over the entire hemisphere and over the all wavelength, right? So that's how we got entire hemisphere and for all wavelength 0 to infinity, right? So let's go to quickly to the question here. So E does not depend on the direction of emission. That is true, okay? Because it has been integrated over all directions, okay? E depends on the view factor. View factor is a radiative exchange between two surfaces. Okay, but whereas E is a surface property. Okay, surface property. So E depends on view factor is false. E depends on the wavelength of emission. As we said, it has been integrated from 0 to infinity for all wavelength. E lambda was, of course, dependent on the lambda, but E is not the total one. So E does not depend upon the wavelength of the emission. So that is false. E does not depend on the frequency of emission. We know the frequency of emission, of course, wavelength is the speed of light divided by the frequency of emission. Since, of course, it does not depend upon lambda, of course, it automatically doesn't depend upon new the frequency of emission, since this is constant. So this is also, see, it says does not depend. So this is true. So this is true and this is true. Okay. So A and D are true. Okay. Before we leave, let's quickly see a chemical engineering application of this problem. Let us say we have a direct fire reformer surface, an ammonia plant, okay, where of course we burn it, the fuel comes in and the flue gas goes out. Let's assume this is around 1200 Kelvin, assuming black body, and of course there's a radiative exchange between the tubes and the walls, okay. Um, so for lambda, if you want to find out the lambda max, we are assuming this to be the temperature here. These are, of course, the catalysts were there. We have discussed it, I think, in question number 29. Maximum wavelength at which emits maximum spectral emissive power if the temperature is 1200. Okay, we have already seen at 1200 Kelvin, I think it's around 2.42 micron. I think somewhere we have seen. We'll really quickly look into it. If so, this is very 2.42 micron lambda max. This is constant at 1200 Kelvin. So this is what the infrared region. Okay, um, so that's what we come in. Second is the spectral radiative intensity. If you want to find out I lambda b, assuming while as a black body, assuming this is very big compared to the tubes. If we assume that, so as we assume that is a black body. If we assume that, so this is given by the Planck's law. We know the value. So this is my H, and this is my C, and this is my lambda, which we have just calculated here. This is my lambda, and this is HC. But there has to be a C here. I think we'll check. And this is a lambda, and this is the Boltzmann constant, and so it's a temperature here, -1. This came out to be around 10 to the 10. That's approximately at 1200 Kelvin. Okay, spectral radiative intensity. Okay, so if you want to the spectral hemispherical emissive power, then we know that it has to be integrated over the entire thing, and then the value was for a hemisphere. This is pi. So if you multiply it by pi, so that gives me the total amount of energy emitted for a particular wavelength micron, so that's more my wavelength over the entire hemisphere. So that's E lambda b. When it is now integrated over into all the ranges of lambda 0 to infinity, then of course gives me the total energy emitted, right? So that's my total energy, assuming this to be a black body, and this of course is given by Boltzmann constant and T to the power 4, and this is a plus. So this is the total radiative heat flux from the furnace one. Okay, so this is what answer. So anyway, so this is just an example, which would be these values are of course will help us to find out. And if we want to find out the actual radiative action, we have to find out the view factor and the temperature of this one and temperature of that one. We'll try to see that kind of a problem later on. But these values help us in doing the furnace calculations. So anyway, the correct answer is A and D, which are true.